What we did last week, we talked about the dissociation. Well, we talked about the polar nature of water after the review of covalent bonding and then the intra and intermolecular bonding and all of that. And we saw that water dissociates. You know, the correct way of putting it is the reaction of water with water. So you have water reacting with water. The collision theory tells you that these molecules are colliding against each other all the time. 99.9999% of the time, nothing happens. But 1 in 10 million times, this is what happens. So you get, in fact, an addition of a proton to one of these two water molecules. And of course, the resultant or the resulting loss of a proton from the other water molecule. And we talked about the fact that this is an equilibrium described by something that we call the KW. Maybe I didn't mention it, but I'm telling you right now. So every equilibrium has an equilibrium constant. The equilibrium constant for the dissociation of water is so important that it has its own name. So it's called the KW. Now, these guys are in the liquid state. These are actually aqueous. So in other words, in water. And equilibrium constants never include liquid state molecules. So the equilibrium constant for these is determined by the concentration of those two in their product form. So in other words, the concentration of hydronium times the concentration of hydroxyl gives you this constant, which is a value regardless of the amount of this.
Is that the H or the O?
Which one? This one?
Yeah,
Oh, I'm sorry.
plus.
This is, it's on the ion. So I tend to put it on the H, but it's really on the ion, okay? In other words, I could put it out there. It doesn't matter. But I understand your question because definitely this negative sign is not on the H, it's on the whole ion, okay? It's on the hydroxyl essentially. Very good question, Stanley, actually, because we assume that certain things that we shouldn't. So that negative sign is not really on the H, it's on the whole ion. All right. Now, we talked about the value of those two concentrations in pure water, if you recall. And we said that the concentrations were 1 times 10 to the negative 7. So I'm not going to put the 1 because it's too long. So those are the two concentrations. And the concentrations have units of molar, moles per liter. Now, when you actually do that calculation, then you know the KW, which again is a constant. And that I'm going to write the whole thing, 1.0 times 10 to the negative 14. And I can put the units, so it's going to be molar squared. These brackets imply molar, so I don't have to put molar, because the bracket implies the units, molar.
I swear, like, the whole they should just have a board. So I'm like I'm looking straight at it, and I just see the TV outside, so I have to like scooch over to like.
Oh, I'm sorry. You want me to move these?
No, oh no, you're not in the way. It's because like if you look at it from this angle, the television that's outside.
Oh no.
Is what's reflecting off of the board.
Yeah,
for me.
and
so if I'm moving around a little bit, I'm just trying to. See.
And remember, if I write here, you can't see everything very clearly. So anyway, so please
Right here.
keep that. Yeah, maybe you want to move over here, John. That would be better. Okay, so keep this in your notes. I'm going to erase it, how we derive
I think
that.
I get that last week, but I'm gonna finish it off.
Oh, it's all right, man.
Can I erase it now?
No.
Not yet? Okay.
Can I ask you a question while like we're both writing
Please,
this?
please do.
And it's gonna end up being a basic chemistry question.
That's
Why the
okay.
brackets for this particular? Why the brackets like for the pH?
The brackets imply concentration.
Okay.
It's not a parenthesis, so it's a very good observation. And it implies concentration in molar, which is mole per liter.
So that's specifically
For chemistry,
for concentration.
concentration.
For
Yes,
for molar.
absolutely.
Okay.
So if I ever write a parenthesis, then I'm contradicting myself because the bracket is what tells you this is, we're talking concentration of in moles per liter. Oh, this is coming up.
It's like just so weird how like what, cause this is a review from last week and I read through my notes before I was reading the chapter.
Well, it is a review.
And why do I understand it when you show it, but like if it's in my face, I'm like, oh my god, what
Well,
the hell is this?
Because I don't think we got this far. So,
Oh, okay.
and
I didn't have it in my notes. Or-
right, I don't think we got that far. I think I defined this, we talked about the KW, but I never put numerical values on that. So
Okay.
now, please keep this value there because it's gonna be useful for the next skill. So can I erase it now?
Yep.
All right.
Oh, thanks for saying that because I didn't write that down. That's all I needed.
So, the other thing that you have to remember from last week is how we define pH. So the definition of pH that I gave you last week was that it's a convenience to work with large, actually in this case very small concentrations in a logarithmic way. So it's defined as a negative log of the concentration of H3O+. Quite often you will see people writing it as concentration of H plus only. Not hydronium, but just hydrogen. In other words, we get lazy and we just write it like that. And that's fine.
It's the same, like.
It's the same.
It's the same thing.
And we're gonna get to that soon. Because actually you can have,
Like, I just want to document that it's the same thing, because like, if I see that, then I will literally get confused.
Right.
On what you thought.
right.
Okay.
So in fact, going forward, I'm probably just gonna be writing H plus instead of H3O plus. Now, you know from last week also that if we put the value in pure water, the pure water value of the concentration of hydronium is 1.0 times 10 to the negative 7. So when we carry out the math, that gives you the pH of 7, the so-called neutral pH. Now, there's another scale that we don't use called the pOH. We never use that one, we don't measure it, but we do calculate it in biochemistry. And if the little p means negative log of, then obviously that means negative log of the concentration of OH minus. And in pure water, this is going to be 7 also. So the pOH of pure water is equal to the pH of pure water, which is 7. Now, based on the KW, you also get another relationship that is very interesting. And this is not in pure water, this is in any aqueous solution. The sum of the pH plus the sum of the pOH is always equal to 14. Okay? So in pure water, we said that this concentration was 1.0 times 10 to the negative 7 molar, 1.0 times 10 to the negative 7 molar. When we calculate the negative log, we get 7, so 7 plus 7, 14. Yes?
Is it? Because I think I've seen this on the homework. Is can you calculate negative log by doing log of that number and then changing the sign?
Yes. So if we calculate this, in fact, let's do it, Stanley. Let's do an example. So let's say that I ask you, what is the pH of an aqueous solution of acetic acid? It doesn't matter what substance. Of a solution with a concentration of hydronium equal to 2.5 times 10 to the negative 4. Okay? So we want to know what is the pH of such a solution. You measure the concentration. The machine does it for us, by the way. The pH meter measures this value and then it converts that into pH. So to address the question that Stanley made, let's put the equation negative log of, and I'm going to put parentheses now instead of brackets because I have the molar units here, of that. So indeed, on your calculator, what you would do is you would put log of that, and it's going to give you a negative number. So let me go to one of my favorite websites. I don't know if you are familiar with Wolfram Alpha.
Oh, yeah.
Oh, yeah.
So that's a good calculator, I think, in general, because it gives you all kinds of log base 10. Remember that is log base 10, and in this case it's going to be 2.5 times 10 to the negative 4. It's hope that Wolfram Alpha interprets this correctly. I don't think it did because I didn't put a parenthesis, so it calculated the log of only 2.5. And I'm not showing you these, you guys, because
Open my calculations.
well, I'll go with whatever results you are, and I think I may have asked you this last time, but I'm going to ask you again. Please bring a calculator home if you have one. If you don't have one, yeah, this is not giving me the result that I want to see. And I normally carry my own calculator. Yeah, now I went to okay, that may be the answer. So what did you get if you guys did it?
3.6.
Okay, so we're gonna put pH equals negative 3.6. You got a negative value, right? I mean, when
I did negative log. I'll show you. Do you want
Oh,
to
you
see?
enter the entire formula. Okay,
I
you're
put
fine.
negative log open parentheses 2.5.
Yes, you did it
times
right.
10 to the
Don't
negative.
worry. But I was addressing what Stanley was asking.
Oh,
So
okay.
if you only put that, you're gonna get a negative
Okay.
3.6.
Yep.
But because you were asking the calculator to do that for you, negative times negative is positive, so the pH of this solution is 3.6.
So Stan was saying if you did just log.
Right. If you ignore the negative sign there and you just do log of 2.5 times 10 to the negative 4, you're gonna get negative 3.6.
Yep.
Okay?
Yep.
So then, that's why we have that negative sign outside. To convert the negative, this is a convenience. There's no other reason. We found out that these are numbers too small to write, 0.00025. So we write them in logarithmic form but we don't want to have a negative number, so we added that negative number there. This is just a definition. Okay, no other rhyme or reason for that. Okay, so now that you know how to do that,
Except for a simple way that non-math people can do math.
maybe. Yeah, that's a good way of putting it too. I don't consider myself a math person, and you're right, I can do it. So it's like, okay, it gives me confidence.
I'm more of a math person than a chemistry person.
I'm more
Which
of
is
a
weird
neither
because
person.
chemistry is all math.
I'm more of a neither person.
Chemistry is all math. If you
I
think
can do
about
the
it.
labs. I can do the labs 100%, but I can't do the math.
So let's do the following, just to wrap these things up. Because there's so many manipulations just with these little formulas that we can have. So I'm going to put the KW again here. And knowing that that is actually the product of those two ions, I'm going to ask you a new question. And you will go, and in fact, you know what? Let's use the same value that we just got just to see if we get it right. So what is the hydronium concentration of a solution with a pH of 3.6? That's the result we got before. So let's see if we get the concentration that I gave you to begin with. So there are two ways of doing this. Well, actually probably more than two ways, but let's do first the math one, which is a little bit, that's the one that Stanley, you were talking about antilogs, okay? So if the pH is defined as the negative log of the concentration of H3O plus, how do we solve for H3O plus? Well, I'm not gonna teach you math, I'm just gonna solve it. Is 10 raised to the negative pH. That's the antilog. And again, I don't wanna go into why that is, that's just what it is. Because we could spend 10 minutes trying to do logarithm rules and you know, we cannot afford it. So trust me that that is the solution of this equation, isolating hydronium, and that's what we need to calculate. So to answer the question then, we need to ask a calculator to do the following for us. What is 10 raised to the negative 3.6? And if you enter the numbers correctly, we should get the same number that we got before, which is what we started with. Not exactly the same number because we probably rounded. So what did you guys get?
2.5 times 10 to the negative 4.
Okay. So we got what we had before. Okay, now, there's another way of doing it, but I'm going to show you that other way by doing the following. Now the question is going to be, what is the OH minus concentration of a solution with a pH of 3.6? So I want you to think about this for 1 minute or 30 seconds and tell me what we can do. How do we answer that question?
14 minus 3.6.
All right, so that's gonna give you what? the POH, right?
Yes.
Very good. So that's one possibility. So Jen is suggesting that we do, well, let's put it in an equation. Since the pH plus the pOH equals 14, I can actually say the pOH is equals to 14 minus the pH. Right? That's what you suggested.
Yeah.
So if we solve that, the pOH is 11.4? No, 10.4. 10.4, right? But that's not the answer to our problem. So now what do? We're gonna do the same thing that we did for the
Antilog?
pH. The anti-log, so now we solve for OH and we say that the concentration of OH is 10, is the anti-log, as Stanley said, is 10 raised to the negative pOH. And that is going to give you an answer that is going to be the answer to the problem. But then we're going to see that there's another way.
Of course.
And you choose whatever works for you, okay? Whatever you feel more comfortable with. The only way to be able to choose is to practice and practice and practice, and then you're gonna go like, oh, it becomes second nature. So what's the OH concentration?
I got 2.51 times 10 to the negative 11.
That sounds right. So tell me the number again.
2.5 times 10 to the negative 11.
And that's molar. Now let's check it out. Let's see if that is in fact the answer. So how else can we answer that question? Well, we know that the Kw is always equal to 1.0 times 10 to the negative 14. It's a constant. So I'm going to put 1.0 times 10 to the negative 14 equals the concentration of hydronium, which we knew from the answer before, right? What was it? I forgot.
2.5.
Times 10 to the negative 4?
Yes.
2.5 times 10 to the negative 4 times the hydroxyl concentration.
Is that parentheses or brackets?
Brackets.
I'm using a bracket. You could use a parentheses and put molar. I'm using a bracket because once again, what we said earlier.
I just, like, I couldn't see it.
Oh, I'm
That
so
was-
sorry. I'm sorry.
It's not your fault, it's the pictures.
Okay, so concentration of OH, let's rearrange it, equals 1.0 times 10 to the negative 14. Actually, if I put the units, it's molar square divided by 2.5 times 10 to the negative 4 molar, and that should give us, it better give us this number. I don't know if it is. If it doesn't give you that number, then we did something wrong, because this is the way to do it. So can you, and remember, when you do this on the calculator, you better put parentheses everywhere, or the calculator is gonna do the operations in the order that it sees them. It's gonna go that times that, and then divided by that, and then divided by that. In this case, it may not make a difference, but sometimes it does.
It's easier to do the parentheses on this calculator anyway because it just, I don't know, like it keeps it all together. Like
Right.
to me it's just easier.
Did you get the same value?
Yeah,
2.5 times 10 to negative 11 or not?
I did.
You did, okay, good. I'm a little concerned because when I do this, it's more like 0.5. something.
What did you have in this?
It gives me the,
Oh, yes.
Mine just like, I don't know, maybe I didn't do it right.
It could be that this number is wrong, but I didn't check it.
yeah, well, that's the basic, like, it's compressed it, like, so it's not an exact,
Right.
but. you
So
know,
what are you
it's
getting?
Still correct, it's like, it's a weird way to write it, but you can still get it.
4 times 10 to the negative 11.
I always thought, like, I'm trying to get it till it's.
So
shown.
was this 4 times 10 to the negative 11 maybe then? Can you calculate again, 10 raised to the negative 10.4? And please tell me that value, because that could be the mistake. 10 raised to the negative 10.4.
Now I have 3.9.
Yes.
Times 10 to the negative.
So that's why we're getting this wrong, because this value is wrong. This is 4 times 10 to the negative 11. 3.9. I'll put 3.9. I mean, I'm sorry, I didn't calculate it myself, so we're just revising our calculation. But if you can confirm that that's the answer, then we're gonna put that number over here instead of this one. Right? No, that one is correct. That one is the answer to this question. So now when we do that, we get 3.9 or 4 times 10 to the negative 11. Gosh, I feel like I'm losing you guys somewhere, but it's simply because I made the mistake of not calculating this myself or confirming that, so that mistake carried over to here, and that's why we were getting a different answer. But we need to get the same answer here and here because we're using the same numbers.
It makes sense.
Some of them are being used in logarithmic form, some of them are used in decimal form, and that's why it looks different, but it's the same thing. Here we use logs, here we use decimals.
So should we do
It
both
makes
steps?
sense to me.
It makes sense to you. What was that?
Should we do both, like, do it both ways?
Always do it the way that you feel more comfortable, and if you want to confirm your answer, then you do it the same way, the second way.
Okay, so that's more like, did I do it right?
Yes.
Double check it.
Yes.
Okay.
And if you get two different answers, then one of the two are wrong. Let's practice one more because I don't want you to be sort of lost. So I'm going to give you a different question. And then of course we need to move on because this is just pH. We're not even in buffers yet.
That's how difficult this is.
Well, it's time consuming and it takes practice. But once you practice, you're gonna gain confidence. So let's say that I give you a concentration of OH minus equal to no, that's what we had before. So let me change it to a 6. 6.2 times 10 to the negative 3. So somehow we were on a different planet where they don't measure hydronium, they measure hydroxyl. Did you guys hear the rocket hitting the comet last night?
Yes.
Yesterday?
I saw pictures of it.
I'm sorry for the total tangent, but that was historic. I mean, if you ever
Was
saw the
supposed
movie,
to hit it? Is
So,
Yes.
Okay.
Yes, it was supposed to intercept the.
have you heard of the movie Armageddon?
Oh,
Well, you know that there is a possibility that a big,
asteroid hits the Earth and
Hits
then
the
destroys the Earth and
Well-
blah, 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 blah.
so NASA, for the first time in history, actually, several years ago, sent a rocket that yesterday hit the asteroid to try to change the orbit.
Yeah, 'cause we had an asteroid coming towards the Earth, right? Yeah.
Well, this one was just an essay. It wasn't a real emergency.
So was like, what, was it like, it was actually like heading in that direction, so they sent it up to destroy it or
To tilt
change
the
its
orbit.
course.
They didn't probably do more than a crater. So yes, it just was intended to change the trajectory, the orbit. But I'm sorry, it was my fault. Let's go back to this.
Yeah.
Yeah, but now
So-
I'm gonna remember what you're teaching because of the asteroid, so there's a point to it.
Yeah. We measure the hydroxyl concentration of a solution, and that's the value we got. Let me put the M for molar. And now the question is, what is the pH of that solution? So I'll take any suggestions as to how you want to approach it, and then we'll just do it. There's more than one way to solve that problem.
Could find the pOH.
Okay, so the first suggestion is find pOH. And then what do you do with that?
Oh, no, that was just
Subtract it from 14.
And then you find the pH. I think you're onto something there. Now, how do we find the pOH? Well, pOH is defined as the negative log of the concentration of OH. So 6.2 times 10 to the negative 3 molar. That's a parenthesis, not a bracket, because I'm including the units.
Well, so it's 10 to negative 3, right?
So 6.2 times 10 to the negative 3, get the log of that, and then multiply the result by negative, and what do you get?
2 point,
Sounds about right.
2 point.
It should be a number around 2 or 3.
I got confused with what you were saying because how I did it was negative log times 6.2 times 10 to negative.
That's
3.
fine, that's fine,
That's
that,
what I
that
did.
works. And what do you
And I
get?
got 2.2.
And anybody else can confirm that? 2.2? So, using your own calculator, please do the negative log of that number, and you should be getting 2.2. That value sounds right to me. But we don't have the pH yet, so how do we find the pH?
14 minus 2.2.
Exactly. So you put 2, find pH.
Yeah, that's why I got 2.207.
Perfect. So we're gonna typically go to 2 sig figs here. 2.27?
No, 2.207.
Oh, okay. So let's round it up to 2.2. Okay. So pH equals 14 minus pOH. pH equals 14 minus 2.2. The pH of said solution is
11.8.
11.8. Thank you. And that's it. That's how you do it. There's no. Can you do it any other way? Yes, you can. You can use the KW, find the H plus concentration. Let's do it over here. So, and then we wrap it up. With this one, we're gonna wrap it up. Okay?
All right, I'm gonna write that, so I don't know if you're.
Please take your time. So I'm gonna put the KW way over here, and we're gonna get the same answer.
I wrote it down, but can I take a picture of that?
You can take pictures of anything you want.
Thank you.
including me.
Strike a pose.
Now, if you sell my picture, then you share the profits.
Sure. I don't need much.
That's only fair.
Stan, I'm gonna probably stand right in front of you.
I just need enough
Okay.
Cause I'm just trying to not get the.
just don't stand in front of the camera. Because other people are going to need to see.
So we have that number. (6.2 times 10 to the negative 3). We solve for H3O plus. And you see how I get sloppy with where I put the plus sign, so please forgive me about that. 1.0 times 10 to the negative 14 divided by 6.2 times 10 to the negative 3 molar square molar. And we're gonna get a hydronium concentration, which then we had to use to calculate the pH. So can you guys do that operation just to make sure that we're using the calculator correctly?
Are we meeting next week?
I don't think so. Let me check the schedule. Yeah, so it's probably a chapter that doesn't have this much math, so you know.
Oh, thank you,
It's
Jesus.
probably the protein, the structure of amino acids. I keep getting Wolfram alpha wrong. So what did you guys get here?
1.61 times 10 to the negative 12.
Negative 12?
12. Yeah.
Okay, that sounds about right. So now we need to get the pH. And we know that the pH is gonna be the negative log of that number, 1.61 times 10 to the negative 12. And it better be 11.8, or once again, we made a mistake.
Whoops. 1.61 times 10. Yep. 11.79.
Or thereabouts. 11.79, perfect.
I'm gonna take a picture of that one too.
So two different ways to answer the same problem using essentially either logarithms or decimal numbers.
Thank you.
You're welcome. All right, so now, time for a new topic, and that's the topic of today, which still is going to use the pH, but it's going to introduce a new dimension called the pK.
The
You know,
PKA or the PK?
It's going to be the pKa for this course, although there's also the so-called pKb. We're going to concentrate on acids rather than bases. So, in generic terms, we can always describe an acid as a proton donor. That's the Bronsted-Lowry definition of acid. Any substance that when placed in water releases H plus ions. Okay? So with symbols, we write it like this. We write HA. Now HA, by definition, is a weak acid. Because we're going to be dealing with buffers, we are not going to talk about strong acids or strong bases and their behavior in aqueous solutions. Their behavior we already know from last week. A strong acid dissociates 100%. So HCl goes completely to H plus Cl minus. But a weak acid dissociates partially. And in fact, just as for water, the dissociation favors the acid, not the dissociation ions. In other words, the equilibrium is shifted towards HA. Now, please keep in mind that this is always aqueous. This is always in the presence of water. So it's not only the acid is in water.
Did you say equal? I have a hard time with that word.
Equilibrium. Equilibrium.
You
I
said
say
that
S,
shifts
but
towards.
it's E.
You said it, the equal, that shifts toward the weak acid. Is that what you're saying?
In this case, the equilibrium is going to be shifted to the left, towards the reactant, if you will. Okay, the weak acid.
Could HA cubed be written ha ha ha?
That's very easy part. Hey, I want to remember that. Ha ha ha.
So if somebody said,
Okay,
does that mean it's
so-
-3?
Let's write the dissociation as little as it happens as follows. And this is again generic. Now, because these are all species in the aqueous state, so this is aqueous, aqueous, and aqueous, we can define something called the Ka, which is the acid dissociation constant, as the ratio of the products over the reactant. So it's going to be the concentration of H plus times the concentration of A minus divided by the concentration of HA. Okay? And every weak acid has a particular Ka, which is constant. Just like water. In fact, Kw is the Ka of water.
What's funny is I don't struggle with this. I struggle with the logarithms.
And the anti-log that you mentioned,
Mhm.
right?
So you said every weak acid has its own.
Its
Ka.
own value of Ka, yes. Water has its own value of Ka. We call it the
That's
Kw.
So
But
if it's like, I know this sounds silly, but if it was like milk, it would be Kn.
Sure. If milk was that important to biochemists, probably
Right.
we would
Yeah,
give
but
it a
I'm
name.
just trying to relate.
No, absolutely. That makes perfect sense to me.
Lactose. KL.
Okay. Okay.
Okay, so now what do we do with this? Well, we can do a number of things. But to give you instead of trying to practice problems right now, I'm going to give you the equation that we're going to use today to prepare a buffer. And I'm not going to go through the development of the equation. I'm just going to give you the equation. You can look it up in Google. The equation is called the Henderson-Hasselbalch equation. And it includes water in here. So how is water included? Well, the Henderson-Hasselbalch equation tells you that you can actually calculate the pH of any solution of a weak acid as follows. So this is nothing but a manipulation of this equation. Okay? Where is the H plus? Right there. Where is the Ka? Right there. We just basically introduce logarithms. So if we take the log of all of these and rearrange it, we end up with this. This equation is paramount in this course. And you know, I better double check to make sure that I have it right, because sometimes if my brain flips terms, and I would hate to.
I wrote it down as PH equals PKA. Yep, exactly.
It
like
is
that.
correct?
Exactly.
Okay.
Like that.
Thank you for double checking that. Now it's interesting because I actually can flip that, and sometimes my brain just doesn't function right. And if I put the HA on top and the A minus, all I have to do is change that to the negative. And that's a logarithm rule. In other words, there's another version of this equation that will read pH equals pKa minus the log of the acid over the A minus. Now some terminology. This is nothing but nomenclature, naming.
PKA is the log of Ka.
The negative log of the Ka.
Negative.
Yes, exactly correct. And I'm getting there, but let me first define some terms that are going to be important for you to do the homework. So if we call this an acid, every acid at equilibrium has something called a conjugate base. Okay? So this is the acid, this is its conjugate base. This is simply the hydronium ion. And we're going to use this equation to make the buffers that I'm hoping we make today. And you're going to be using it in the homework for other problems. The challenge problem uses the Henderson-Hasselbalch also. But before that, let's do some theoretical questions regarding names, these names. So I'm going to see if I can fit it down here. Now, phosphoric acid is somewhat of a strong acid. It's not a very weak acid. It's actually somewhat strong. But it does have an equilibrium. It is not like hydrochloric acid. It doesn't fully dissociate. It partially dissociates. Now, when this dissociates, imagine what would result if I remove one proton, one H. What am I going to have on this side?
Isn't it H2PO negative?
Okay. So, wait. Melissa, quick question. Could you go from this? Oh, okay. Well, then I'll just okay. So then I'm gonna send you an email later today or tomorrow so that I can look it up the manual. But yeah, that's fine. Okay. When do you think that will be? If you will let me know, maybe I'll.
Me too.
That would be awesome. Okay. I'm not meeting with them next week. Okay. You leave it on that. Oh, God bless you. Thank you. Oh, great. Thank you. Okay, so I guess the DNA sequencer is not set up, so we're not going there, which gives us more time for this today. But we'll go there.
So are we still going to prepare a buffer?
We are. We are going to prefer the buffer here, yes. Absolutely. Okay. So, absolutely right, Stanley. But let's put first the hydrogen by itself. and then you tell me what you just said, okay? So I'm gonna put H plus, that's the one that I removed, and then you said H2PO4, right? I think that's what I heard before I rudely walked away. Sorry. I didn't want her to
Wouldn't there be a negative on top of the 4?
Exactly. And you know what, let's be clear, -1. That's important because, so let's look at this equilibrium, compare it to the generic one, and if this is the acid, this is the conjugate base, correct?
Yes.
So the H2PO4 is the conjugate base of H3PO4. Well, it turns out that this can dissociate 2 more protons. And it dissociates 1 proton at a time. So, there's another equilibrium. I'm gonna run out of space, but I can put it on the bottom. And do you guys care to predict what is the next conjugate base?
HPO -2 over 4 over 5, wouldn't it?
HPO4
Yes, over -2.
-2. Correct. Absolutely. And then that one can dissociate 1 more time.
Jeez.
To be PO3 -4.
Exactly right. I'm sorry that I had to do it that way, but so what we have done is remove 1 proton at a time, or well, we didn't do it, but nature did it.
For that very, very last one, it's H plus 1.
It should be H1 plus PO4 3 negative.
H1 plus PO 4. Thank you.
So let me just make another statement, and then I'm going to ask you a question. So if this is the acid, this is the conjugate base. But if we ignore this dissociation and we look at only this dissociation, if we concentrate on this, if somehow we could isolate it, then this guy is the acid and this is the conjugate base, correct?
Huh?
Whichever has the less protons of a couple of substances is going to be the conjugate base.
So
Whichever
they're not
has
all the conjugate base? The
not in relationship to others. So that's why it's important that you understand this. Let's concentrate, ignore what happens after this. So let's just concentrate on this part.
Okay.
Right now we're just ignoring that part. If you look at this equilibrium, that looks just like the generic one, right?
Sorry.
And terminology-wise, this is the acid, this is the conjugate base of this acid, right?
Yeah,
It's just-
yeah,
we're
that
just
makes
naming
sense,
them.
yeah.
Okay.
Yeah, no, that makes sense.
Now, if now I ignore this reaction and I look at this equilibrium, the one in blue. Now we have H2PO4
Oh!
dissociating into H plus HPO4 2 minus. In that equilibrium, this guy is the acid and this guy is the conjugate base. How do you know? You always look at the protons. Whichever has more protons is the acid. Whichever has less protons is the conjugate base. Always in pairs, by the way. And finally, if we only concentrate on this last reaction, HPO4 2 minus is the acid and PO4 3 minus is the conjugate base. Now this is the scary part. Scary because it can be a little
Because it's
intimidating.
biochemistry.
Each of these reactions has its own Ka. So this guy has a Ka1, has a Ka2, has a Ka3. Because this substance actually can yield 3 protons.
Well, it does, doesn't
It
it?
does. It
Like-
does. So you always need to know what you're dealing with in order to figure out what substance you're dealing with. Because see, this substance doesn't exist in biochemistry very much. But this one does.
What is that?
This is sort of like this with only 1 proton to yield. So it's gonna have its own pKa. Don't worry about that right now. I'm just telling you there is a functional reason for us to look at this, a practical reason rather.
Can you take a picture of this?
Yes.
I'm trying to do it this way because, like, if I look, like, reflect back to your.
I'm actually, you know what, Jen, and I don't know if it's gonna work, but I'm taping this stuff on my phone.
Oh, are
So
you?
I'm gonna upload it. I hope it works. I don't know.
I didn't know there was a camera.
My apologies. I can delete you. I mean, I can edit.
Yes.
Edit.
And
you
if I
out.
check you better out.
In place of that fragment, I'm gonna put a NASCAR.
You should. Or a Cincinnati Bengals logo.
Okay. So is that clear? This terminology. This is just naming. Okay. Because one of the problems in the homework is gonna ask you precisely to do this with a different substance, sulfuric acid. All right. So now, let's take a look at how we can use the Henderson-Hasselbalch equation. And in this case, I hope I can use this. Let's take a look at the challenge problem. And then we're gonna make the buffer. The battery must be weak because it takes a while to.
What time is it?
Yeah, 12:13. So if you need to step out for a few minutes, or if you
I just
wanna.
need to grab some water for a second.
So you wanna take a 5-minute break, and then
I
we do the
need to
problem?
like get a couple of sips of water because I have to keep
Okay.
drinking it.
Go ahead then. I'll pause for a second, and maybe I should do the same.
Definitely. Stay hydrated.
My God, it's such a chronic problem not to be hydrated. And I think it's for
wondering
everyone.
if we could like, even like just us, if we could look at like the first question on the quiz.
Absolutely. I'll open it before we make the buffer, we'll open that question. Absolutely. In fact, let me start looking at it now. On the quiz for this week or for last week?
This week. We don't have to do like the same numbers, just like
Okay. No,
Something.
that's all right. I mean, we can modify the numbers a little bit.
Oh wow. That's so hard. My back is bad.
That's the question, Stanley?
yes.
Okay, great. I mean, in fact, we can start with that instead of the challenge problem. Okay? So, maybe I can, raise,
Is this homework?
this is a quiz for this week.
Oh.
And that's the first problem. So Stanley was asking if we could take a look at it, and I think it's the perfect thing to look at. Oh Jesus, you can hardly see it. So you're gonna have to trust me with the numbers that I'm gonna put here. I'm just gonna copy them.
Can you go like with that program? Can you go into the quiz and go out of it, or do you have to do it all at once?
I set it up so that you can go back.
Oh, okay, that's right, you did.
I don't wanna time it, I don't wanna, you have the week. And if you need more time after the week is over, you just tell me and I extend the deadline. The point is, to learn this stuff. So it says there, what is the ratio of the conjugate base over the acid at pH 2.7 put 2.75 of a substance known as formic acid. Before I give you the other piece of information which is given to you in the problem, let me just ask, do you guys know where is a natural source of formic acid? I actually had a professor in Virginia and his last name was Formica. So Formica. In Spanish.
Is that like the countertops?
Oh, that's for
Formica.
It's spelled the same, isn't it?
Yes.
I didn't know that. Well, it's Italian, so it's Formica. In Spanish, this is translated as hormiga. Formica, hormiga. If you speak Portuguese, it's probably close to that. I don't know. That means ant.
Because I was gonna say that was my guess, because ants have formite.
So ants, when they bite you and it burns, one of the things that is making it burn is formic acid. So just a side note. And it comes from the word in Italian, in Latin, for ant, which was sort of close in other Romance languages, but kind of far away in English. I don't know what the origin of the word ant is. Who knows?
It's probably anti-other language because it's not like any other.
Okay, so the problem in the quiz also tells you that the pKa of formic acid is 3.75. So the pK, they don't call it the pKa, but I like calling it the pKa, is 3.75. For formic acid, not for any other substance. Okay, so they want to know this value, which if you look at the Henderson-Hasselbalch equation is this value right here. So that's a little bit tricky when you do math. So how are we going to do that? Well, my suggestion is that we don't convert this equation into decimal. We put numbers and then we do the anti-log. So let's do that. So I'm just going to take this equation as it is and put the information that I have in the problem straight into the equation. So 2.75 equals, that's the pH according to the problem, 3.75 plus the log of A minus over HA. And please notice that it's not asking you for the value of A minus or for the value of HA, it's asking you for the ratio of the two. Getting the value of A minus and the value of HA is possible, but it's an extra step. Well, let's manipulate what we can to simplify this. If I move this right here to this side, I'm going to have 2.75 minus 3.75 equals log of A minus over HA. Simple algebra, right? I just rearranged it. I moved this to this side and put the negative sign. So if I carry out that operation, now I have -1 equals log of A minus over HA. Now, to make this more visually pleasant, I'm just going to tell you that in my brain, this works better. I'm going to call that fraction, that ratio, x. I'm just going to call it x to make this look a little bit less intimidating. So I'm going to move this over here and rearrange it. So I'm going to say log of x, it's log base 10, but I always forget, we always forget, equals -1, right? That is this flipped with my shorthand notation. I cannot forget that x means that. I'm not solving it, I'm just saying it. So now it's hopefully clear to you that what you have to do the antilog is going to be x equals 10 raised to the -1. So the antilog is 10 raised to the value of the log. So the answer to the problem then is the concentration of A minus divided by the concentration of HA is 10 to the -1.
Silly question time.
Ah.
So, I have a silly question.
Okay?
So the anti-log can, like, it's whatever, like if that, say log x was 4, like a positive number.
10 to the 4.
So
would be that.
anti-log, you don't switch that to the -4, right? That's,
No.
okay, alright,
You take the sign of the number.
okay,
Okay? The reason why we put the negative pH before is because actually that's by definition negative log. This doesn't say negative log. So
okay. I just want, I will get confused.
So
Ah,
how
oh,
would
it's
we
very
write
easy.
that? How would we draw that?
Uh-huh. So, let's bring this down. And let's see how. You're asking a tough question because I don't know if I... So, what is the ratio? They only want the ratio, so we're just going to put 0.1 and that's it. Can I submit just that? Oh, there's several questions, so let's just answer all of them. Then they want the structure of HA for formic acid. So I think formic acid is 1 carbon. Oh, let me look it up. I don't even know it. It's a carboxylic acid, that's for sure, but I don't remember the number of carbons. Oh, only 1. Doesn't get any simpler than that. So, let me put it here as a reminder. I guess that's formic acid. Okay? You need to think back to last week. This guy right here is not an acid. This is a covalent bond. Sorry, let me put it over here. So this is important. When you look at the structure of formic acid, You need to think back at last week. We said that any bond between carbon and hydrogen is considered nonpolar, and that hydrogen, because it has no polarity, cannot be removed. It's covalently very strongly bound. However, this guy has polarity. So this acid, the hydrogen that it loses, this is the HA, is going to be this one.
Mm-hmm.
So if this is HA, generically speaking, that whole thing is this guy. A minus, this guy is going to be that. This thing minus that. So the A minus for this one is going to be C double bond O H O negative sign, negative minus 1. So this is a formate. That's another terminology thing. The conjugate base of an acid changes its root from ic to ate. Acetic acid, acetate. Phosphoric acid, phosphate. Formic acid, formate. So this is the formate ion, which is the A minus. This is the formic acid, which is what we're gonna try to enter. And boy, you guys are gonna test me on this one because I'm not very good with this molecule drawing tools. It always takes me several attempts to get it right. So they want the HA, so let's see, carbon. Okay, that worked. We need to connect the hydrogen to that with a covalent bond. So let's see what happens if I click on the H and on top of the H. No, it changed it. Never mind. Okay, covalent bond. Oh, for goodness sakes. Let's see. No? Is it implied or what?
I think it's implied.
It's implied? Okay, it is implied. So it's using the skeletal structure. So now we need a double bond on that atom, and we need an oxygen there. Thank you, Stanley, that did it. And then we need an OH, right? So another single bond on that carbon, and oxygen here, single bond, hydrogen, and that's formic acid. Yeah, so it's not. Okay. And now they want the conjugate base of this acid, and we already know that all we're gonna do is remove that and put a charge of -1. Okay? I wish you could just copy this and paste, but how did we start? We started with a carbon, then a double bond. Let's put the oxygen. I know you're not having fun. I'm having all the fun here.
Oh yeah.
Hydrogen, and then single bond, oxygen, and then I have no idea how to put the negative sign. Should I do more?
Oh.
Oh, there we go.
Yay.
Negative sign. Okay, that works. Thank you. So now that's the conjugate base of formic acid, or formate, and this is the acid, formic. So we have one more part of the problem to answer, and that is what is the function, what is the fractional charge on the acid at the given pH? Oh, wow.
I think that question goes with question 4, but I don't know how to answer that question.
Question 4 or this question?
Both.
So,
I think
so this
that-
one is similar.
Yeah, I think so.
Okay, I'll open it in a second. So let me take a look and digest that. Okay, so let me raise the screen because this requires a little bit of a manipulation of what we already have as an answer, as a fraction, as a ratio. Okay. So please bear with me. We need to do the following. So we know that the ratio of A minus to HA at a pH of 2.75 is 10 to the negative 1. Let me put that in decimal. It's just gonna make things a little bit more clear. 0.1, right? 10 to the negative 1, 0.1. Well, if I rearrange this, if I move this to here, I'm gonna have the following relationship. Let me put it over here. I'm gonna have the concentration of formate equals 0.1 times HA. Now think about that for a second. And let's take arbitrary values. If I assign a value of 10 to that, arbitrarily, if I say this is 10, what is A minus? 10 times 0.1 is what? 1. So, what I want you to realize is that this is 10 times smaller than that at that pH. Okay, so arbitrarily speaking, if I put a value of 10, then A minus equals 1. That's the ratio of 0.1. In other words, 1 divided by 10 is 0.1, right? And that's what we had over here. So no matter what this value is, this is going to be 10 times smaller always. So if this is 20, this is 2. If this is 0.1, this is 0.01. So on and so forth. So what is the question asking? Let me read it again.
What is the fractional charge on the acid of the given
At a given pH. What is the fractional charge on the acid at a given pH? I'm trying to digest that statement. So the fractional charge,
I'm not the only one who's confused.
well, I don't like the word fractional, so I don't think they're expecting a value. I think this is, the way I ask these questions is as follows. At a pH of 2.75, you have 10 times more acid than the conjugate base. In other words, if I put the equilibrium again, if I put this, the amount of that and the amount of that changes with the pH. Okay? Now this is something interesting, and to write this down. When the pH equals the pKa, only under those conditions, the amount of HA and the amount of A minus are the same. Okay? So, at a pH of 3.75, at a pH of 3.75, not 2.75, a pH of 3.75, this would be equal 1.
3.75.
If I rewrite the problem, erase from your mind the 2.75. If I put here 3.75, and I do the numbers, and because of what I just said, when the pKa equals when the pH equals the pKa, this ratio is equals to 1. And that comes from Henderson-Hasselbalch. If the concentration of that is the same as that, 1 divided by 1 is 1, log of 1 is 0, so the pH equals the pKa. At a pH of 2.75, on this equilibrium, we have more of this than of that. How many times more? 10 times more. In other words, the equilibrium is favored in that direction. There's 10 times more of this than of that at a pH of 2.75. That's what this number is telling us. I don't feel like I'm making my point.
It would be 1 over 10.
So that's what I'm trying to determine if he's asking for a charge. I mean, obviously, there's more of the positively, or the neutral, 10 times more of the neutral species than of the charged species. Is that right? I mean, we have 10 times more of that than that at this pH. The equilibrium is shifted towards the acid, not towards the base. So let's try that, Stanley. We're saying 1 in 10. You know what? Let's see what they're expecting, because this is confusing me.
The only results when I searched for fractional charge was about like quantum mechanics, which I don't think is
No,
possible.
we don't want to go to quantum mechanics. No.
This is confusing enough.
So let's see.
Does the book itself like plot these questions?
Yeah.
So like they didn't give you like a whole like way to set it up. This is like their chapter 2 quiz.
Right.
They're messed up.
Yeah.
Okay, hold on.
No wonder why I was so confused, because like I'm like doing the homework last week and I'm like cursing him. Like now I know it's not his fault. This book is just ridiculous.
It's the wording that is
Confusing.
right, misleading, I would say.
I think the wording was
Reveal
confusing last
answer.
week too. A little bit.
I think I know what they're asking. It's kind of a useless type of question, but in a way, it's also very revealing. So let me see if I can put it here. I'm gonna erase this stuff. And actually, this is gonna prepare you for the next chapter, because amino acids are tricky, and amino acids still rely on your understanding of these Kas and pKas and that kind of stuff. So.
Amino acids are found in biology, they're probably not in biochemistry.
So if I put formic acid, I'm just going to use the formula for formic acid.
So you're probably way better prepared for this class than me, because I took the 113 and 114. Because that's what my anxiety
I'm not prepared for my career, so there you go.
Okay. So that's formic acid and its dissociation. Before you put this in water, when you just have pure formic acid, the charge is 0, because you don't have any of these. You only have these. So there's no charge on that molecule, right? Now, if I combine this with water, and never mind the concentration, if I just add some water, this equilibrium is going to start happening. Now, if I add water so that I get a pH of 3.75, then the amount of this and the amount of this is equal. which means the charge, the fractional charge as they calling it, is negative 0.5. Why? Bear with me. I think I'm onto something here. If this could dissociate 100%, in other words, if this hydrogen, if this could happen, nothing left here, all of it, 100% like that. The fractional charge would be negative 1 because there's none of these left and all of this is there. Is it making sense?
No.
A little bit? Not yet. Okay. So think of the dissociation of formic acid. Formic acid has one hydrogen that can be given up. If I tell you that, this is hypothetical, it doesn't exist by the way. If I tell you that formic acid can completely dissociate, separate into ions, so that you have 0 of these and 100% of these. In other words, all of these became that, then the charge, the fractional charge is negative 1, because that's the charge of the ion. Okay? But if I tell you that only 50% dissociates,
Oh, okay, I get you. I get you.
if I tell you that only 50% dissociates,
Mhm.
then the charge, the fractional charge would be
Negative
0.5
Yep,
negative, because that's a negative value.
yep, I get you.
So-
Now I get it.
So when we have, what was it? What did we say? 90% and 10%? Guess what? Negative 1 times 0.1 or 0.1, which is 10% in decimal, gives you negative 0.1. And that's the answer that they have. So that's what they were looking for. They actually have it to more than one significant digit. So it says 0.09, I think. Yeah. So if we report this to one significant digit, that is negative 0.1. That's the value that we're getting.
So if you put 0.01, they would put it as wrong?
Oh my God, let's try it again. That is a very good question.
Like, cause,
Retake.
well, that means you have to do that
Let's
whole
see.
crap.
I'm just gonna do that one. What was it? Negative
0.1.
0.
Cause what was it, 0.09?
Right.
Yeah.
Right. And let's submit. Submit final answers.
Oh, so it wasn't wrong.
It wasn't wrong.
Cause it's not highlighted,
It
right?
marked this wrong. It marked this wrong, that wrong, and the first one wrong because we left it
Yeah.
empty. But this one is not highlighted as wrong, so they took that.
Okay.
You see, this is an introduction to biochemistry. In an advanced biochemistry course, in fact, in an analytical chemistry course, the reason why you get a value of 0.091 is because they probably use the quadratic equation. Remember the quadratic equation? Horrible. A and B and C.
Oh, yes.
That.
X equals negative b plus or minus the square
We,
root.
we are not gonna go there. And my apology. There you go. Wow. Okay, so quantum mechanics and now the
Are
quadratic
you an
equation.
engineering major?
I was in astronomy before this.
Oh, okay.
I'm about to hand the markers to you and say, come and teach me that. No, seriously, thank you for those contributions. But Stanley, thank you for bringing this problem up, because this is going to give us a little bit of more understanding what terminology they're using. So now, before we do the buffers, I want to look at that problem 4. So now it's not going to let
Can
me
you-
take it again.
Can it reset you? You're the professor.
I think so.
like,
It should.
like, Like, if it
Okay,
doesn't,
let me close
I'll
it and
stick
open
with
it again.
Hope it didn't mess you up, I'm sorry.
No, that's okay. I'm sure I can reset it somehow. Okay, review, questions complete. And what happens if I say review, my attempt, feedback? Are you serious?
That's probably about my biochemistry score, 75 out of 12.
How do I? Okay, let me see if I can click on question 4. Oh, it is opening it. So I'll take care of the other problem before. And then let's see, question. Okay, we're just gonna see the question. Okay. So is this the one that you were thinking is related? Okay, so let's try to solve this one. And forget about the challenge. The challenge is gonna be easy compared to this problem. And actually this is gonna take us nicely to making the buffer, because you need to understand the concept of moles in the context of concentration. So as a matter of fact, before even we look at that problem, let's talk about concentration. And very quickly, I'm gonna go and see what solutions we have.
That's
Okay.
needs notes.
So before we address that other problem, let's talk about concentration in molar so that we can make that buffer today and put the Henderson-Hasselbalch equation to the test. Boy, I went up. Okay, so molar is defined as moles of solute per liter of solution. Because there's another concentration unit known as normal. And then there's also molal, not molar, but molal with an L at the end, which would be liters of solvent. So we don't want to go there. We want liters of solution. So if you want to prepare, let's start easy. A zero. Well, let's do it even easy. A 1 molar solution. Of, if we do it for formic acid, just because we've been using it, what you will need to do and let's make it easy again. To prepare a 1 molar solution of formic acid with a total volume of 1.0 liters, how much formic acid do we need? So if you remember, the molar mass of any substance is its weight in grams per mole of that substance. So roughly speaking, you guys remember the atomic mass of carbon? What's the atomic mass of carbon, roughly speaking? 12. So atomic number 6, mass is about twice that, 12. Hydrogen, what is that? Rounding it off to 1/6. 1. Oxygen, I can tell that you work in the lab. 16, 15.9, so 16. So, if that is the case, the molar mass of that is gonna be 12 times 2 because of the carbon plus 1 times 2 because of the hydrogen, so I have 2 hydrogens, and 1, 2, 16 times 2 because of the oxygens. So the molar mass of formic acid is 34, 38, 58, and the units are grams per mole, which tells you that 58 grams of formic acid are 1 mole of formic acid. So if we want a 1 molar solution, we want 1 mole per liter, right? Molar moles per liter. 1 molar, 1 mole per liter. And we want 1 liter, so this is super easy. All we do is to prepare that solution, we need to weigh 58 grams of formic acid and add water to 1 liter until you have 1 liter. So you weigh your formic acid and you start adding water until you get 1 liter. The resulting solution is 1 molar. If you want to prepare a 0.1 molar, that's 0.1 moles, which means 58 times 0.1, that would be 5.8 grams in 1 liter. The volume remains the same. If we wanted a half a liter instead of a liter, then you need to divide 58 by 0.5. Let me see, let me think about that. No, yes. So you need half of this in half the amount of water. So whatever 58 divided by 2. 58 times 0.5 will give you the amount, and then you add water to 500 mLs and you have a 0.1 molar, sorry, a 1 molar solution. Okay, so that's molarity concentration for you. How is that? Oops, can I erase it? Okay. So, does that relate to Henderson-Hasselbalch and to our preparation of a buffer today? Well, we need to define 2 more ideas here. So what is a buffer? I'm not going to write the definition, I'm just going to tell you the definition. A buffer is a substance that can prevent drastic changes in pH. But it can only do so to a limited capacity. It's not infinite, it's not eternal. Okay? So, there are many buffers. Because when you do biochemistry, let's say that you're trying to understand an enzyme, and that enzyme comes from E. coli, and E. coli lives at a pH of about 6.2. So the optimum pH for that enzyme to work is going to be a pH of 6.2. So what you want to do is you want to prepare a buffer to study that enzyme in the lab that keeps the pH around 6.2. How do you do that? Well, it's actually Henderson-Hasselbalch. Remember what I said before about the pKa when the pKa equals the pH, you have 50% of the acid and 50% of the conjugate base. So in other words, if you mix 0.1 molar acid with 0.1 molar base, you get a pH equal to the pKa of that substance. And every substance has a pKa. This sounds convoluted. You're gonna need to do the homework and the quiz to digest all of this information. It's a lot of information. Hopefully, if the video works, you can watch it again. I'm not responsible for the captions because they're gonna be automatically made, and with my accent, one word that it always gets wrong is acid. The auto caption thinks I'm saying that.
Asset.
And that's of course because of my A's and my E's and my A's or whatever. So anyway, so there is a lot of buffers out there, but in biochemistry there's a collection of buffers that are known as good buffers. And if you finish this course and somebody in the future asks you, do you know what is a good buffer? And you say, yeah, a buffer that really works very well. I'm gonna come back, find you, and chastise you. Because good in this context means the last name of Dr. Good. So Dr. Good was a biochemist who came up with a list of buffers that are used in biochemistry. They happen to be good, but they're good for biochemistry. So Good is the last name of Dr. Good. One of the most famous good buffers is called tris. It's widely used in biotechnology for extracting DNA, for running gels, and I have it right here, tris base. So there's tris base and tris acid. Because we don't have the tris acid, we're just gonna use probably hydrochloric acid if I can get my hands on it. And if not, we're gonna go through the motions. So what information do I see in this bottle? Well, unfortunately, and we can look it up, I don't see the one that I wanted to see. So pass it around, and there's a formula, and then there is a formula weight. On that side is the molecular weight, right? So I'm gonna have to Google, well, actually you guys do me the favor, if you have a phone, can you Google the pKa of tris base, T-R-I-S. What's the pKa?
K-R-I-F.
Mm-hmm.
T-R-I-S.
8.1.
8?
8.1.
8.1.
At 25 degrees Celsius.
Thank you, both. Okay. Now, what does that mean? Well, it means that at a pH of 8.1, I'm going to have 50% of that and 50% of that. Here is another thing that you need to write this down. I mean, you need to write down and never forget. Any buffer is useful at a range of pH of plus or minus 2 from the pKa. In fact, some people are so particular that they say plus or minus 1. In other words, tris is going to be at its best, so it works best at a pH equal to plus or minus 1 away from the pKa. So, if you're studying an enzyme that works best at 8, oh, this is the best buffer. It's right there. If you're studying an enzyme that works best at 7, you can still use this because that's within 1 pH unit of 8. If you're studying an enzyme that works best at 9, this is still your buffer. But if you're looking at an enzyme that works best at 4, you better find a buffer that has a pKa of around 4. So to summarize, buffers work best at a 1 or 2 pH units away from their pKa. You want to select a buffer on the basis of their pKa value. So, today what we're going to do is we're going to simplify our lives. And we are going to, I wish we could find tris acid. You don't recall seeing it? I don't think so. Because then if we have tris acid, we can add 0.5 moles of one, 0.5 moles of the other, and we're gonna get a pH of 8.1. Exactly. So let me just think about this for a second. I think my point is not necessarily to test the Henderson-Hasselbalch equation, but for you guys to prepare a buffer. So let's just prepare the buffer. And we're gonna prepare 4 different solutions, and we're gonna measure the pH of the 4 different solutions, and then bring them all to pH of 8 by adding HCl. And then remeasure the pH, of course. I'll tell you what we're gonna do. So just give me one more minute with this. So any questions about this? How you calculate the molarity of a solution if you have the formula weight, the molar mass? You do it like what we did for formic acid. So each of you are going to be doing your own calculations when I give you your assignment in just a few minutes. But let me just wrap it up with the following information. So, we're going to put Henderson-Hasselbalch here. Okay? And if we had the acid of this base, that would be this substance. What we have in that bottle is this substance, A minus. That's the base of an acid called tris acid. Now, we know the pKa of tris. It was 8.1. Let's say that you want to prepare a buffer solution to study an enzyme that works best at a pH of 7.5. So, prepare a tris buffer at 7.5 and we'll talk about the concentration in a minute, but you already know that that's your target. So what information do we have? It looks like we have very little information, but in fact we have more than what we need. I mean, just as what we need. So, taking this pH, which is what we want the pH of the buffer to be, we're going to substitute right here and say 7.5 equals, well, we know the pKa of tris base, right? So we're going to put 8.1. And then we're going to say plus the log of x, because I don't want to be manipulating that. Remember that x I'm defining as A minus over HA. And I'm just gonna put that back here when I finish. I just don't wanna be confused, okay? So, log of X equals 7.5 minus 8.1. Did I do that right? I sort of flipped it, and then I moved the 8.1 to the other side. So log of X equals, what is that, negative 0.6? Is it negative 0.6? I hope I'm doing that right.
Yep.
Okay? So now X equals 10 raised to the negative 0.6. So can you guys do that, please? I need to bring my calculator. X,
0.25.
X equals 0.25.
That's what I got.
Okay, can somebody confirm that value? 10 raised to the negative 0.6.
Yep, 0.25.
0.25, perfect. So we have a confirmation. All right. So that means I'm gonna now replace the X with what I put over there, that the concentration of A minus divided by the concentration of HA has to equal 0.25. I just replaced that. And now I can actually say that the concentration of A minus equals, if I move that to this side, 0.25 times HA. Okay? We're almost there. This happens to be tris base, that stuff in the bottom. So I'm gonna put the concentration of tris base is gonna be equal to 1/4, 0.25, of the concentration of tris acid. So in the end, it turns out that we have all the information we need to make a buffer that will have a pH of 7.5 by combining for every 1 part of tris base, for every 1 mole of tris base, we're gonna combine 0.25 moles of tris acid. Now, unfortunately, we don't have tris acid. So we're gonna do the buffer, but we're gonna do it differently. And we're not gonna do it with calculations. I'm just gonna give you different amounts to each of you for you to prepare. Now, how much and what molarity? Well, typically these are dilute solutions, so never more than 1 molar, never less than 0.01 molar. So 0.1 molar sometimes works good. So that means 0.1 mole of these for every 1/4 of a 0.1 mole of that. Okay, 0.25 times 0.1. Now, that's from Henderson-Hasselbalch. If you were to combine exactly 1 mole of these with 1/4 of a mole of the acid, and you were to stick the pH meter in there, you would create a pH of 7.5. That's awesome, in my opinion. But we don't have the acid, so if there's no questions, I'm gonna now charge you with the activity of making your own buffer. And we have about 40 minutes to do that. I think we can. So questions about this? I know you probably have many. I still meet via Zoom. So even next week when we don't meet here at 11, I will be in Zoom at 11. So for you guys to come and ask questions. All right? And then on top of that, my office hours, and on top of that, if you need time outside of that, we can arrange for that. But not having to meet here doesn't mean that I will not be available at 11. All right, so here comes the assignments.